Here in part 2 of lesson 70, we will look at examples related to the fundamental theorem of calculus and also the definite integral. From the investigation, you'll learn that the limit at infinity of the Riemann sum that gives the exact area on a curve between x equals to a and x equals to b is known as the definite integral. According to the fundamental theorem of calculus, if f is a function on the interval a and b, and if uppercase F, the big F, is any antiderivative of the function f on this interval, then we can say that the definite integral of f of x d of x from a to b is equal to substituting b, the upper bound, into the antiderivative minus substituting the lower bound a into the antiderivative of the function f. Below is a list of useful properties of definite integrals. First, you notice that if I have the negative of an integral, we're really looking at switching, the lower bound and upper bound in our order of operation, in our subtraction. And then if I want the definite integral between an interval from a to a on a continuous function, it is 0, because think about it represents the area, there's 0 area within that particular interval. And then the next part tells you that if you're taking the integral or definite integral of the composite of two functions being added together, you can actually add the results of their individual definite integrals of f of x and g of x. And then if you're really talking about a continuous interval from a to c, from c to b, then you can evaluate the whole integral all at once by taking the very beginning of this interval from a to the very end of this interval b. Let's start looking at example 1. Evaluate. So here, I noticed that maybe it's easier for me to rewrite the first term in this function as x to the power of 1 plus 1/2, which is 3/2, minus x dx. I will find this in antiderivative first. So x to the power of 3 over 2 plus 2 over 2, which is 5 over 2, divided by that, minus x squared over 2. And then I know that because we're looking for the definite integral, we now have to evaluate these antiderivatives at 0 and 2. Starting from the upper bound, I have 2 over 5 times 2 to the power of 5 over 2 minus 2 squared over 2. And then I have to subtract the first term when I evaluate it at 0 and when I evaluate the second term at 0. Okay, now how do I simplify this? Here I have 2 to the power of 1 times 2 to the power of 5 over 2. This is really 2 to the power of 7 over 2 over 5. We'll get back to that. 2 squared is 4. This is 2. This is really 8 root 2 over 5 minus 2. Here is example 2. All those square roots look very distracting. So I'm going to first rewrite my expressions. So root 2 x to the power of negative 1/2 minus, I have square root of 1 over 2, but I will change it into root 2 over 2 times x to the power of 1/2 dx. This allows me to factor out a square root of 2 before I take the antiderivative of the expression. Okay, here we go. First term, we have x to the power of, bump it up by 1, it's positive 1/2, divide by positive 1/2, we get 2. Minus 1/2, that's the original one, multiply by x to the power of 1/2 plus 1, so 3/2, and then divide by 3/2, that turns into 2/3. There we go, and then our boundary is 4 and 1, from 1 to 4. I will first reduce the second term by 2. And now I can actually evaluate this part. Okay, substituting the upper bound first. I have 2 times the square root of 4 minus 1/3 times the square root of 4 to the power of 3 minus 2 times the square root of 1 minus 1/3 times square root of 1 cubed. I would just show it for the sake of showing my work. You can skip this line or the one substitution if you like later. Okay, so square root of 2 times, I have, what do I have here? Square root of 4 is 2, this is 4. Cube root of the square root of 4, so 8/3. Okay, minus, well, those are all ones, so I have 2 minus 1/3. Okay, that's not too bad. Let's move to the side to continue. So I have square root of 2 times 4 minus 2 is 2. Negative 8 plus 1/3, oh that's nice, plus or minus 7/3. Well, 2 is 6/3, so I have negative 1/3, negative root 2/3 is my final answer. Now let's take a look at example 3. Evaluate, then check the answer using a GDC. We're looking for the definite integral of 2 sine x dx from 0 to pi. Finding the antiderivative of 2 sine x, I get 2 cos x, but negative. Okay, and we're evaluating this from 0 to pi. Substituting the upper bound, I have negative 2 cos pi minus the substitution with the lower bound, but I'm subtracting minus negative, so this is plus 2 cos 0. Cosine pi is negative 1, so that's positive 2. Cosine of 0 is 1, so plus 2. I get 4. You can access the definite integral function by using the math menu, and then number 9, function integral. And you can enter your expression. So we're going from 0 to pi, and then the function that we have is 2 sine x. So 2 sine x, close brackets. And then we are finding the integral with respect to dx. Enter. The answer is 4. Another way to do this is graphically. If you go to y equals and enter your function 2 sine x, close brackets, and then press enter, you can set your window from, say, negative pi to pi, and then you can use whatever scale. I'm going to use pi over 2, and then let's use negative 3 to positive 3 for y min and y max. Here is the graph. We're only interested in from 0 to pi, correct? So let's go to second function trace, where you'll notice 7 gives you the option to calculate the integral. Lower limit is 0, upper is pi, enter. It will show you the area between the curve and the x-axis and also the value of the definite integral, which is 4. The very last example in this lesson asks us to show that when you evaluate the definite integral of x plus 1 dx from 1 to 4, it is equal to evaluating this integral from 1 to 2 added to 2 to 4. Here it shows the screenshots on your calculator. When you compare the left side of this expression in the very first graph, okay, look at the interval given compared to having 1 to 2 plus 2 to 4. Okay, so the area would be equivalent. We can also show this algebraically. So let's look at left side. When I evaluate this, the antiderivative x squared over 2 plus x from 1 to 4. Substituting 4 into the expression first, I get 4 squared, 16 over 2, 8, plus 4, minus 1 over 2, plus 1. So this is really 3 halves. This is 12 minus 3 halves, so 24 minus 3, 21 over 2. If I do this on the right side, I will follow very similar steps and have x squared over 2 plus x from 1 to 2 added to the same expression going from 2 to 4. What do I have here? 2 squares 4. 4 over 2 is 2. 2 plus 2 is 4. Minus 1 over 2 plus 1, 3 over 2. Plus, substituting 4. 16, 8, 8 plus 4 is 12. Minus 2 squared is 4. Divided by 2 is 2. Plus 2 is 4. So 4 minus 4 is gone. I have 12 minus 3 halves, which is exactly what I got. Therefore, left-hand side, it's equal to the right-hand side.